I am Rudraishwarya Banerjee and my presentation topic is a shared aperture KU-Ka band feed source for a high gain fixed beam offset parabolic reflector antenna. Often SATCOM employs reflector antennas at their terminals for their high directivity and relatively low cost. But a reflector has a single focal point for feed placement, so it is a challenging topic to design a dual band feed that covers two far off frequency bands for transmit and receive purpose in SATCOM applications. On the other side, circular polarization is also required for SATCOM applications. Therefore, keeping SATCOM application in mind, here a Fabry-Perot based fixed beam shared aperture dual band microstrip array that works in Ku band and Ka band is proposed. The Ku band and the Ka band array are designed in such a way that the antenna has same phase center for both Ku band and Ka band so that they can be placed at the focal point of the offset parabolic reflector antenna. Here a circular polarized single element at Ku band with single layer PRS is presented. The separation between the substrate and the superstrate is given by this equation. Therefore, when n equals to 1, the height which is applicable for Ku band, the same height, same PRS height is applicable for Ka band when n equals to 2, where n is an integer determining the mode of resonance. Therefore, a same PRS is applicable for Ku band as well as for Ka band when n equals to 1 for Ku band and n equals to 2 for Ka band. Now when we see the single element radiation pattern, we can see that the element pattern minimum is at 88 degree. Now the position of the first grating lobe of the array factor is given by this equation. Therefore, if the inter-element spacing d is chosen in such a way that this theta GL occurs at the element pattern minimum, then the grating lobes can be significantly reduced. 2x2 sparse array at Ku band with 2x2 Ka band conventional array at center is shown in this slide. The D that we calculated from previous slide is found to be 22 mm. But here we have chosen D equals to 25 mm so that we can accommodate the Ka band array at the center of the sparse Ku band array. The technique of sequential rotation is applied for both the bands to achieve a considerable axial ratio bandwidth. The Ku band sparse array works in right-hand circular polarization, whereas the Ka band array works in left-hand circular polarization. This is the Ku band array and this is the Ka band array, which we can see from these configurations. A cross-shaped defected ground structure is employed for both the bands to improve cross-polarized fields. Here we have presented the fabricated prototype and compared the simulation and the measurement results. This is the antenna in the anechoic chamber and this is the zoom in view of the antenna, the top view, the bottom view and the antenna with the PRS. Here we have shown the reflection coefficient versus frequency and the axial ratio versus frequency and the radiation pattern at 14.5 GHz and 25.5 GHz for the Ku and the Ka band. Considering 3 dB axial ratio criteria, we can see that the array covers a bandwidth of 500 MHz in Ku band and a bandwidth of 1 GHz in Ka band. Here the shared aperture array with PRS is placed at the focal point of an offset parabolic reflector antenna with f by d equal to 1.5 and d equals to 50 cm. The reflector size is 25 lambda at Ku band and 50 lambda at Ka band. A peak gain of 30 dBIC is achieved at Ku band and a peak gain of 35 dBIC is achieved at Ka band, which we can see from these two radiation patterns. Therefore, in conclusion, here an innovative design technique of a feed source suitable for a parabolic reflector working in two far-off bands with 1:2 ratio is proposed for SATCOM applications. This concept can be applicable for any two far-off bands for transmit and receive purpose, provided a proper PRS material height and thickness are chosen. Thank you for listening.